Yeah. Hi guys. Let's wait a couple of minutes before we start.
Hello, and welcome to the postgraduate program.
A couple of minutes before we start. Okay. Yeah.
Hello.
So yeah. Hi guys. Today we will be discussing the problem and the solution to the problem Blackjack from January Long challenge. The challenge ended today at 3 p.m. I guess. So yeah, this is the video editorial for the problem Blackjack. Okay. Let's see. Challenge ended today at 3 p.m. I guess. Yeah. So let's start with the problem first. Problem statement. So chef is playing a card game called Blackjack. He starts with a deck of n cards. So we have n cards numbered from 1 to n. Each valid ith card has integer ai. Okay. So every card has an integer on it, ai. Then he starts dealing the cards one by one in the order 1 to n. Okay. So he wants at some moment in time some of the cards dealt so far. So some of the cards dealt so far, he wants them to be between x and y. Okay. So some of all the cards, some of the values of a on the cards dealt so far, he wants them to be between x and y at any moment of time. So if this never happens, chef loses. So we want chef to win the game. So without him noticing, we will swap some pairs of cards. So initially we had cards in order 1 to n and values a1 a2 dot dot an, and now we are going to swap some pairs of cards before the game starts. We want to find the smallest number of swaps we need to do so that chef can win the game, or determine that it is impossible to make chef win. Okay, so this is the problem statement. Okay, so let's see the constraints. We have test cases. N, x and y are up to 1000. Yeah, so 1000 cards, values up to 1000, and the sum also, it's important to note the sum also we want it between x and y, and that is also up to 1000. Values are also up to 10,000, all are 1000, all are positive. Sum of n over all test cases doesn't exceed 10 power 4. Cool. So subtasks, fine, we will solve the whole problem. So yeah, so let us write the problem in our terms. Yeah. Okay, so we want at any moment. So first of all, chefs dealing cards one by one. So basically at any point of time we would have a prefix of cards, a prefix set of cards. This is one point. So at any moment of time we would have a prefix set of cards. So basically we want some prefix sum to be between x and y. That is actually the main problem, I think. So we want the prefix sum, any prefix sum, first prefix sum, second prefix sum, or any prefix sum, we want it to be between x and y. Okay, so you can assume that you are given an array a1 a2 dot 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 an. So we can even ignore the cards. We are given an array a2 up to an, and we want one of the prefix sum, any of the prefix sum of it to be between x and y. That's the aim. And what operations we are allowed to do? We are allowed to make swaps. So basically we can swap any pairs as we want, but we want to minimize the swaps, minimize the number of swaps. So we want to minimize the number of swaps. Cool. So this is the problem statement. I hope the problem statement is clear. I am not audible. Are you sure? Okay, sure. Also let me share my screen on this. Sorry, I did not share screen here. Screen one, I don't know, application window. I'll share this one only. Okay, cool. So yeah. Okay, so basically we can say that we are given an array. We want to make one of the prefix sum to be between x and y, and we can do swaps. So, and we can do any number of swaps as we want. So that's a pretty concise statement, I would say. Yeah, so we can start observing some things, or maybe analyze some cases. So we can start with that. So in the end we have a prefix, we want a prefix, we have a prefix to be between x and y, prefix sum to be between x and y, right? So let us fix the length of the prefix. Let us fix the length of the prefix and then start analyzing the cases. Let us fix the length of the prefix. Okay, so let's say the prefix length is I. Okay, so we are talking about ith prefix. So basically, after all of the swaps have happened, we are going to take the starting I cards, and we want it to be between the sum between x and y. Okay, so let's say initially no swaps have been made. Okay, so currently no swaps are there. The cards are like this only. The array is like 1, 2, 3 up to n. So now we are going to do some swaps. Okay, so let's talk about the swaps. Let's say the swaps are from within. Let's decompose it into two sets. First is 1 to I, and then there is the remaining one. Okay, because we have fixed the length of the prefix I, that's why I am decomposing it into two sets. So let's say the swaps are here only. Let's say the both of the positions of swaps are inside of this only. So that doesn't let me write it. If swap happens inside of left set, nothing changes. Why? Because the prefix sum remains the same. If we swap elements, if we swap a pair between this only, among it only, nothing changes, because the prefix sum we are concerned about is starting I elements. So the set of the starting I elements, that hasn't changed, so the sum is also the same. So it hasn't changed, so why would you waste a swap? You wouldn't, right? Similarly, if a swap happens completely from the right set, if swap happens inside of right set, then also nothing changes, because we are going to take only first I elements. The elements from the second right set, they don't matter to us. So I don't care what order they are in, they are getting shuffled or not, I don't care, because I am not even going to count them. So the only case we are concerned with is a swap one element from the left set and one element from the right set. That is the only swap we are concerned with. Only swap which changes something is one that spans both left and right sets. One element from the left and one element from the right. Yeah, because that is the one that that changes the prefix sum. So let's say we remove one element x from here and insert one element y from this right side. So our sum decreases by x and increases by y, right? So yeah, so we observed that the swaps have to be between right set and left set. So basically we can remove even the swap terminology. What we can do is we can say that we are going to replace some of the elements from left set with some elements from the right set, and that is also, maybe we can write it as replace. So the operation that we can do is replace some elements from left set with elements from right set. From one replacement I am talking about, from right set. So we can say that we are going to replace some elements from left set with some elements from right set. So this was one observation. So basically we reduced the swap thing, and we reduced it to a subset replacement. A subset of this is going to replace a subset of left side, right? So there is that. So yeah, so let's see about that. So now we also want the final value to be between x and y. So maybe let's fix that as well. Let's say that final value is w. Okay, so let's say that the final value is w. So what would happen is, let's say we have two sets, left subset, I would say left subset and right subset, that we are swapping. Okay, left subset is getting swapped with right subset. So what would happen is, currently we have some, let's say prefix sum would be, let's say, let current sum is without any swaps, current sum is S. Okay, so let's say that the current sum is S. So what would happen to the prefix sum, right? So currently it is S. When we swap the left subset out of it, we reduce the left subset sum, right? Okay, so currently it was S. We reduced some elements from left side, so left subset sum got reduced, and we introduced elements from right side, so we increase the sum by this many right subset. So this is the final sum, and this has to be equal to W, right? Because we have fixed it, it has to be equal to W. So basically we want this. Okay, so this is what we want. Cool. So what we can do is maybe we can rearrange it a bit, and then we will I mean, I am going to rearrange it because we have two variables here, left subset and right subset. So it's better if we move them to opposite sides, so that you'll see we can we can compare things, right? So let's switch them. Okay, so it can also be written as W minus S plus some left subset. This is equals to some right subset, right? Oh, I missed one condition. The number of elements in left subset should be equal to right subset, because we want to swap, right? So doesn't matter which one is getting swapped with which one. We just care about the number of elements. They have to be same because we need 1 swaps. So length of left subset should be equal to length of right subset. So this is it. So what did we fix? We fixed I and we fixed W, and we want these two things, right? So this, we want this to happen. So I hope this is clear. We didn't choose I value. Actually, we are just iterating over every value. We are fixing, I mean, we would iterate over I, the value of I. Okay, so these are we are going to iterate over I and W. That is what we have currently fixed. Yeah, these are the two variables that we have currently fixed. Okay, so so what we can do is maybe we can also simplify it a bit more. So what we can say is that we can, instead of since what we are doing is we are skipping some elements here and we are taking some elements from right side, let's take elements only from both the sides. So what we can do is we can let's say what I'm saying is that if we are skipping some elements, let's say 5 elements from right side are going to be introduced here, so I minus 5 elements are going to be remaining the same, right? Because 5 from here are going to replace 5 from here, the remaining I minus 5, they are going to be the same. So what we can write it as W minus S minus some left subset. So I mean these equations, these are, I mean, I'm just rearranging them, so you can directly think of that way. Like what we are doing is we are picking some elements from left, picking some elements from right, but the number of elements in total that we pick, that should be I only. So you can think it like that way. I will write that. So we are picking some elements from left and some from right. Total elements equals to I, should be equals to I. So basically this is what you can think it of this way. So this S minus this left subset, it was getting skipped, right? So S minus some left subset, this is the remaining sum. So we can say that we can write it as some left subset only. But what some left subset currently means now is, it means that these are elements that I'm going to pick. Okay, so I will, yeah, so W minus some left subset, this is equals to some right subset. So you can think it because of this line. So we are going to pick some elements from left. So let me write it like this: some left subset plus some right subset. Okay, so let's think of this line. Some elements from left are picked up, some elements from right are picked up. Total elements we have to pick up is I, and yeah, left subset sum plus right subset sum, that should be equals to W. So I was writing it this way because I want them to be on opposite sides, so that we'll compare them in the end. Yeah, it will help. So this is the equation, and this time we have this plus this is equals to I, right? because total elements we are going to pick up is I. Okay, so earlier I was just picking some 5 elements, let's say, from here and replacing them with 5 from here. Now what I'm doing is I am picking I minus 5 elements that I will keep. The remaining 5 will be replaced by 5 elements from here. Okay, so nothing has much changed, just the representation has changed. Okay, so now what do we want? So basically now we can start formalizing the solution a bit. So since we are concerned about the length of the number of elements we have chosen in our subset, so we have to take care of that, and the number of elements we have taken in the right subset, so we have to take care of that as well. Okay, so basically we have to keep 3 things, I think. Yeah, we have to keep 3 things. So let's say this is from the prefix and this is from the suffix. Why prefix? Because this is from 1 to I, and suffix because it is from the remaining I plus 1 to n. So let's call 2 things. We have prefix I, then what do we have is, let's say, L, the number of elements that we have chosen in our set, and let's say what we want sum. So let's say S. So what it means is can we choose L elements from prefix of I elements with sum S. So this is, let's say, we are formalizing the datas we are going to use. So this is true or false. This is going to be true or false. So this says, can we choose L elements from prefix of I such that their sum is S. Okay, then similarly we can do for suffix also. Okay, so can we choose yeah, that would be exactly the same. Let me just copy it. Can we choose L elements from suffix I to n, let's say, I plus 1 to n, let's say I to n. Okay, I to n with some S. Okay, so these are the 2 definitions so that we want. So but you can see that I can go up to 1000, L can go up to 1000, S can go up to 1000, but we will worry about the optimizations later. Let's it's an n cube currently, so let's try to work with this and find the solution. So yeah, so this right side expression seems pretty okay, because the suffix is enough, I think, for this one, because I have length right subset that in my DP, you can say we have I also in our DP that we fixed, and then we have sum also in our DP. So the right side expression is covered with this suffix, but the left side expression is not covered. This one is covered, but this W is not covered. So what we can say is that we can modify the prefix one. So we are going to modify the pref. So what it means now is, can we choose L elements from prefix of I elements? It's going to be changed very slightly. Prefix of I elements such that W minus the sum of them is S. Okay, why we are doing this? Because we want to, in the end, we want to compare them for equality, because here we can, I mean, earlier it was with some S, here we want W minus some S to be this, right? So we can modify it like this way. So what it means is, we started with W and we went on and chose a subset of length L from the first I ones, and W minus the sum of the subset chosen, that is equal to S. Okay, so this is the definition we can have. So now what we can do is, we can simply in n cube, what we can do, we just want to see what we can do is, for every I, once we have processed this prefix and suffix, this suffix and this prefix, we can simply calculate our answer as, for every I from 1 to n. So we iterate over every I, so the position that we are fixing, then for every L from 1 to n, this is the number of elements that we are going to choose from the left side. Okay, then we are going to fix the sum also for every S from 1 to n. So this is, I am talking about the n cube solution. So we are just iterating over everything. So from left side, we have pref I, L, S. Okay, so we have pref ILS, we have pref ILS, so this should be equal to, so if pref ILS, so that means that I started with W and I chose L elements and I subtracted them from the sum from the W and I got S. So that should be equal to, if I chose L elements from the left, I have to choose I minus L elements, right? We had the condition, yeah. So I have to choose I minus L elements from right. So suffix L, we have to choose I minus L elements and the sum should be still be S. So this S is here and this S, remember that it is W minus the sum of them, right? So we started with W. So it's if we talk about it, you can see that it's exactly actually 10 power sorry, n power 4, right? Because we are fixing W also, right? Okay, so we are fixing W also. So what we can do is, instead of fixing W, we will see about that. So currently it is n power 4. So now let us do some optimizations. So one optimization you guys might have seen is that since this is a Boolean array, I hope you guys, I can explain, but yeah, knapsack problem, kind of a knapsack problem it is, right? Choose L elements from I elements that sum up to S. So we can do this, we can optimize it, since we are keeping only true and false, so binary digit 0 and 1, so we can optimize this using bit set. So let's first work with optimizing these arrays. So suffix ILS, let's work with optimizing these arrays first. So how can we optimize it? So now this S, this is not going to be another dimension, but it is going to be a bit set. So let's say we have a bit set of 1000, because we have sum up to 1000. We have pref 1000, 1001. The definition is going to be the same. Still we have pref ILS, the definition is still the same, but yeah, instead of storing it into an array, we have stored it into a bit set, because array would have 10,000 elements, but bit set would be implemented using 1000 by 32 elements, because one element, 32-bit integer, that will store 32 values instead of just one value. Okay, so that's so this way we would reduce memory as well. So how much memory would it take? 1000 into 1000 into 1000 by 32, because it is not stored digit by digit. We have internally, it would have been stored as an 32-bit integer. So one integer would store 32 values, 32 Boolean values at once. So total these many integers would have been required. So this is the this is the memory complexity. So the definitions would still be the same. So yeah, okay, the definitions would still be the same. So how do we process this? So we can see the transition for this. So how can we process this one? So yeah, so remember that in let's process the suffix first, that is a bit easier, and then we will look at the suffix one. So suffix ILS means that we from suffix I to n, we want to choose L elements with some S. So we can assume that the later suffixes I plus 1, I plus 2, those are processed. So we will make use of it. So let's what we can do is we can simply check if suffix I plus 1 satisfies this, or suffix, or what we can do is I can take the ith value into consideration, and the remaining I can take from the later ones. So what I would do is I plus 1, I take one element, therefore I reduce it by 1, and the sum gets reduced by the value of that element position, so it is reduced by AI. Okay, so what it means is, at first I did not take the ith element, I just asked the I plus 1th suffix, and in this case I took the element and I asked the I plus 1th suffix for the remaining set. L minus 1 elements I have to take now, and S minus AI should be the sum. So we can do it this way. So in case of bit set, what we can see is that it's let's say we have in case of bit set, this can be simply represented as a left shift. So bit set, let me tell you what operations it performs. Bit set performs AND, OR, XOR, left shift, right shift, left shift and right shift. These are the operations it performs. and ORs or left shift and right shift. So I want to access the see, you see that for every s we have to shift it by AI units to the right. So let's say, let me give you an example. We have let me take a big bit set: 8 7 7 6 5 4 3 2 1. Binary numbers are this way, right? The least significant digit is on the right side, most significant on the left side. So let's say that currently it is 1. Let's say that currently let's yeah, we'll see, yeah, 0 0. Okay, and let's say it's 1 0 0 1. Okay, and this would be 1. Sum of 0 is always achievable. So what does this bit set mean? This bit set means that I am able to get 1, I am able to get 4, I am able to get 7. Okay, so this means that. So in the second part, what we are doing is we are taking AI. What it means is that I have taken AI for every s, irrespective of s, we are shifting it towards right by AI. You can visualize it like this way. Like let's say I have taken 3. I have taken 3 already. So what is the remaining thing that I want? So that would be how can I explain this? We can say it like, so actually we want to operate in this only. We want to eliminate this s thing. So basically currently we are saying that, okay, so whatever the I plus 1th suffix has, that I also have, but I have to consider myself as well. So what I'm going to write it, I will write it and I'll then explain. Yeah, suffix of I plus 1 L, I plus 1 L minus 1, because I am going to consider myself now. Okay, and that would be right shift AI, I think. Yeah, right shift AI, because I have to OR it. Yeah, suffix of I comma L or suffix of I plus 1 L minus 1, right shift AI, I think. So let me make sure if it is left shift or right shift. 1 second. So when we left shift, we actually reduce the value. So yes, we want to reduce the value. So yeah, I guess. But so basically the thing is, the I plus 1th suffix, whatever values it was able to reach, I am going to add AI to them, right? Yeah, I am going to add AI to them. So that's why I am going to do this right shift. Okay, so currently it means that we can discuss it now. So let's say that currently I was able to get 7, I was able to get 4, and I was able to get 1 and 0. Now I have an extra element 3. So what all the values I can get now? So I can get, earlier I was able to get 7, so now I can get 10, right? So I am going to make the new bit set. So now I should be able to get 10, I should be able to get 7 we already got. So I mean, whatever we were able to get before, that is still should be possible. So that still we would be able to get. So we were able to get 7, sorry, then 4, then 1 and 1. So this was, we were already able to get. What about this extra 3? How much did it help us? So 7, with 7 we can take 10. So because 7 plus 3 is 10. Then 1 plus 3 is 4. So 4 we have already taken. 0 plus 3 is 3. So now 3 is also. So this is the final, this should be the final bit set. Okay, so how did we reach this bit set from this bit set? So I am going to this is the way actually. So what this is doing is, this is adding AI, in our case 3. This is shifting everything by 3 bits. So this is actually, all of the bit set got shifted by 3 bits. So this is actually, everything got shifted by 3 bits. Yeah, 10 9 8. Yeah, so actually this is the this should be it. So 0's value, it got shifted to I did not shift it to 3. Yeah, I have to shift it to 3, 11 and 10 and 98765. Yeah. Okay, so now you can see 0 was 1, so now 3 is 1. So you see whatever values were earlier possible, now plus AI values are possible in this vector. So let's say we had 0, so 3 is possible. We had 1, so 4 is 1 now. We had 4, so 7 should be 1 now. We had 7, so 10 should be 1 now. So basically we just shifted it by 3 units. That means that we added 3 to all of these values. So basically we shifted the Boolean array by this. So I hope this part is clear what shifting and addition means. So addition in bit set, it means shifting to the left. So we are adding, so we shifted to the left. So these are the all values possible now. So suffix il, it wants to know what values are possible, right? So whatever I plus 1 values are possible, we can simply write it like this. Whatever I plus 1 was possible, and whatever I plus 1 L minus 1 was possible, but I'm going to take my element, right, AI, so I will shift it to AI. So this will give all of the bits set in suffix il. That will tell me about the values that I am able to get. See, yeah, the values that I am, it would tell me the sum that is reachable, that we can achieve by taking L elements from suffix I to n. So this is the so you can see this is OR, this is left shift. So let me write it. Bracket is important. Yeah. So this is OR, this is left shift. So all of these OR and left shift, etc., all operations take n by 32 time. Yeah. So if you know bit set, you must know that all of these operations take n by 32 time. So this way we were able to process suffix array not in on per transition. We were able to do it in on by 32. So currently we have n cube by 32. So this is fast enough. You will see this is fast enough. So bit set, this thing I am removing, this is how bit set works. So yeah, I will keep it here. So this is how we processed suffix. Okay, but now we want to process prefix. So we have prefix il. So prefix il is a bit different. It's not what the sums are achievable, but it's w minus the sums that are achievable. So whatever was achievable up to L, that plus whatever, plus I am going to take myself, so this is going to be L minus 1, but instead of adding I am subtracting, right? So I am going to shift it to the right. Yeah, just that, just w. So I must give you the base case. So what base case would be? Prefix of 0 comma 0, that should be equals to w, 0 comma 0 comma w, that should be 1, because we started with w. Our sum was already w. We started with w, and then we are subtracting the values and seeing what all possible values we are able to reach. So this is the base case. So for our suffix base case, that would be suffix base case would be suffix of n. Yeah, this would be the last suffix, and size 0, and 0 should be 1. Yeah, because initially the sum was 0 for suffix. For suffix we are keeping the sum directly, but for prefix we are starting with w, right? We are starting with w and we are subtracting and seeing what possible values we are able to reach. Because why we are subtracting? Because this is the left side of expression, right? So okay, so that we were able to do. So yeah, so for a fixed w, yeah, so let's talk about how, I mean, the processing is optimized. Processing is not taking n cube now, it is taking n cube by 32, but still we have this we have fixed w, and still we have this n cube loop. So can we optimize here? So let's see. So basically what we want is, you can see that s the prefix il and suffix I minus l, both are subsets, both are bit sets, right? And we are checking if both of them have a common bit set. You can see, yeah, we have to it's not even that, I have to write prefix il s, that is true, that double equals to 1, so it should be 1. Yeah, so basically we are checking if in both the bit sets we have sth value, the value at sth bit, sth position, if both are 1 or not. So what we can do is, we can avoid this loop, we can avoid checking one by one, we can simply take and of it. So what were the vectors? Prefix il and suffix I minus l. Prefix il and suffix I minus l. So these are the two bit sets. We want to check if they have a common bit set or not. So we can this is a new bit set. let's call it bit set. Set is equals to, this is a new bit set, and then we have a bs.any. This any function also we have that tells us if you have any bit set or not. So basically you would now be able to check if there exists some s for which this bit set and this bit set both have a value 1 on it. So this any will give you one value, a value 1. So if both of them have 1, the and would also have 1, and this bs.any then would give you the will tell you about if we have a common bit or not, and that we want to check, right? So if bs.any, so if we have this, I am going to update my answer. So answer is equals to, answer is the number of swaps, right? So answer is equals to minimum of answer comma, we want to minimize swaps. How many swaps did we do? We chose L elements from the left side. So remaining I minus L, they have to be moved to the right, and suffix we choose I minus L elements, so they have to bring to the right. So I minus L swaps, right? Because L is the number of elements we were keeping. I minus L is the number of elements we were keeping we were jumping from right to left. So I minus L swaps have to be done. So, but this still, we have this W, we fix the W. So how do we do that? For a fixed W, now we have n square and n by 32. So we have an n cube by 32, but for a fixed W, okay. So for a fixed W, we have an n cube by 32 solution, but we cannot do this for every W 1 by 1. So one trick you can see is that in the base case we started with only one value W. What if we start with all of the values from x to y? So what I'm trying to say is that we can say that currently we don't have one value, we have a set of values from x to y. From that set, what are the possible values we are able to reach? Not only from W, but from all of the values. So all of that can be handled together, we don't need to do that one by one. So yeah, I mean what we are saying is setting it for every W from x to y. So we are going to set 1 for every W from x to y. So what it means is that currently we are starting with the set. The set contains values from x to y, x plus 1, x plus 2 dot y, and from those values we are going to subtract the subset, the sum of the subset, right? So we are going to see what possible values we are able to reach. So that is one optimization that reduced, we don't need to do it one by one, we can do it together for everything from x to y. So that is a big optimization. So let me see if you guys have any questions. Let me check the link as well. I'll explain a bit more, but let's see about questions.
Need a professional website? I created one for our startup.
Check the link as well. I'll explain a bit more, but yeah, Karan, it's a big problem.
I created one for our startup.
So actually, okay, so let's summarize, then you will see it's not that much. So we can summarize again. So the thing is, I was explaining bit set, and also you might have thought it, but yeah. So basically we had an array, we wanted to do swaps. So and we wanted a prefix to be with the corresponding sum between x and y. So you thought that the swaps, internal swaps don't matter, only these kind of swaps from left to right, they matter. So what happens is some of the elements from this are going to replace the elements from here, right? So what we did was we just there is a lot of stuff that we have fixed, like we have kind of did a lot of brute force here, maybe you can say, because we fixed I, we fixed the W, and then we fixed the sum also. So you can see yeah. So instead of picking the subset that we are going to replace here, we are going to move out, we picked the subset that we are going to keep. So let's say if we are going to keep 5 elements, the remaining I minus 5 elements, they have to be moved out. So when they will be moved out, so I minus 5 elements from here, they have to be picked up. So that part is here. So L elements from left are kept, so I minus L elements remain there, that have to be moved out, that have to be replaced, and they will be replaced by I minus L here. Okay, so this is IL and I minus L is that part. So but how are we simply equating S and S? So the meaning of prefix and suffix is a bit different. For suffix it is we want I minus L elements to be picked up. Sorry, this should be I plus 1, I think. Yeah, this should be I plus 1. Yeah, because suffix now is starting from I plus 1. Yeah, so yeah, correct. So we want I plus 1 to n, we want to choose I minus L elements from there, and we want to swap it. So there is that. And initially the value, I mean, we want the value to be between x and y. So from the left side we took the value w and we fixed it. It is from between x and y. So we thought that we would be making this value, this w value we are going to make. So that this s for prefix is this one, and s for suffix is this one. That's why we initialized w1. Yeah, so we did this. So we started with w and we subtracted. So we left shifted. So basically we subtracted. So yeah, so basically we subtracted different AIs and saw what all possible values we are able to get. So these are s's we are able to reach from left side. These are the s's, and these are the s's from the right side. So we saw that. I mean, this is a good trick. I think that you calculate what possible values of left expression you can get, what possible values of right expression we can get, and then if you get a common value, then you know that you have reached a solution. So when we reached a solution, we took where is it? When we reached the solution, we took the minimum answer of minimum value, whatever we wanted. Answer equals to minimum of answer comma number of swaps. Number of swaps we have I minus L, because yeah, I minus L elements will be moving towards left side. So yeah, so instead of just fixing w, we can process all of the w's together. So it doesn't matter, because we just have to update the base case. So we just set w for every x to y. So basically what we are having is, we are processing all of them together. We are starting with all the values x to y, and we are subtracting subsets from all of them together. So if they initially they were from x to y, so this left shifting is going to subtract ai from all of them, right? Because all of the bits get shifted, so this is subtracted from all of them. So whatever values we are reaching, we are able to reach from some value from x to y only. It is nothing, it is not going to be outside of x to y. So if let's say if this is true, if this is set to 1, prefix I ls, what it means is, we started with some value between x and y, between x to y, and we chose a subset of L length, and the remaining value that we had, that is going to be coming from the right side, that is s. So that's what it is. So whatever we were going to keep, we subtracted out of it, we subtracted from it, and the remaining one is going to be coming from the right side. Okay, so whatever we could get from the prefix, that we have already subtracted, and now it's turn for the right subset to bring up the remaining value. So the remaining value is this s. So remaining value has to be brought from the right side. So this is one way we can implement it. It's not very code heavy, so we can implement it as well. So yeah, let's try it. We have test cases. Okay, so we can also discuss one more approach. Yeah, we can have one more approach. Maybe that would be less tricky. This involves a lot of stuff, I would say. Yeah, I would agree. Yeah, this involves a lot of analysis and then optimizing, and specific type of formation of this condition, like rearranging it, and then yeah, optimizing it. So but yeah, let's code it anyway. Bit set we have bit set 1000. Okay, so actually we have almost pretty much coded up here only. You can see the intended solution. We can post it. It's almost this one only. I mean, some of the solutions you can see it would be this much only. We can discuss on the approach. I think, yeah, we should discuss another approach. I mean, problems have a lot of solutions, so maybe we can discuss another one of them. Yeah, so let's discuss another approach, another solution. Yeah, so this solution had time complexity n cube by 32. N cube by 32. So this was the time complexity. So you can see that it passes. It's not I mean, it passes in 1 second fast enough, I think. The next solution that we are going to discuss is yeah, it is a bit based on observations. Yeah, but not, we don't need bit set for that. Okay, the first part is the same. We fix I. We fix the subprefix length that we are going to take. So basically we fix I. So yeah, let me copy this. So we fix I, and the observation that swaps only these interleaving swaps only they matter, that is still true, that is always true. So what we want is we want let's say final sum from left side is SL, final sum from right side. These are after swaps. Why I'm saying final? Because these are after swaps. We would not care about the number of swaps right now. Don't worry about that. So final sum from left side would be SL, final sum from right side would be SR. Okay, and we want SL plus SR to be between X and Y. That is what we want. SL plus SR to be between X and Y. Right? I guess that's the only thing that we want. Yeah. So after swaps this happens, right? Okay. So after swap this happens. So basically we just want for every I we want this. So let's say we have two things. Let's say we have DPF. So for prefix let's say prefix, we have two things, I and S. What it means is I'll tell you what it means, and then we have suffix I and S. So let's say currently it means that from first I elements, can I get a subset whose sum is S irrespective of the number of elements? We removed the number of elements thing from that. So it just means that can I get a subset from first I elements whose sum is S? Okay, and let me write it. Can I get a subset from first I elements whose sum is S? Similarly, from the suffix part, can I get a subset from maybe we can say last I elements? Sure, last I elements whose sum is S. Okay, so this is the definition, let's say. So let's say that yes, I am able to basically what I can do is I can iterate, I can fix I. Now we are going to do brute force I from 1 to n, and whatever issues arise we will solve them. And for the left SL we will fix SL 0 to whatever it can go up to. It can go up to Y, let's say. So okay, so what it means is we fixed the prefix and we fixed the sum from the left side. So the remaining sum from right side, that has to be between. So if we fix SL, then we can simply say X minus SL. SR has to be between this range. Okay, so that is there. So basically what we want to check is if suffix I plus 1, okay, because I have already used in prefix. If suffix I plus 1 has any value set between this range X minus SL to Y minus SL. So currently I told you let's not worry about the number of elements to be equal. Let's not worry that these are like let's say there are three elements missing from here, but here we have 5 elements. How do we swap them? Let's not worry about that. We will discuss about it. So let's just worry that the total sum has to be between X and Y. So basically we fix the left side sum, so the remaining side sum has to be between X minus SL to Y minus SL. Just simple, yeah. So that's what we want, right? So what we can check is we can check it one by one, but since it is a range kind of thing, right? Because X is fixed, X and Y are given in input. SL we are fixing, so this value is fixed, right side value is fixed. So basically L is equals to X minus SL, R equals to Y minus SL. So basically we want to query from L to R. What we want to query in suffix of I plus 1. So we want to check if suffix of I plus 1 has a value set in L to R or not. Basically that we want to check. So you can see that suffix of I plus 1 is always fixed for given SL. We can see that LR are changing, but suffix I plus 1 values are always fixed. So we can even build a segment tree on it. So build segment tree build segment tree on suffix of I plus 1. So what does that segment tree give? That segment tree gives whether you have a value set between a range. In a range, if you have one value set or not. So you can we can have that, of course. Segment tree can do that. So we build a segment tree on suffix of I plus 1 and just simply check. We just query. This would be login, right? Because we are now querying. So if we are able to get a value, I mean, if there exists such SR such that it is between this range, then we know that yes, we can have a kind of solution, but we didn't care about the number of swaps, right? So because that is our answer, so let us bring that into the statement. So earlier what these definitions were, can I get a subset from first I elements whose sum is S? Now I am going to change that. If yes, what is the maximum size of it? So instead of boolean, I am going to check what is the maximum size of it. Why I am interested in maximum size? Because I want the number of swaps to be minimum, right? Therefore, from prefix, as many elements as I keep, as beneficial for me. I want to keep as many elements as possible. Whatever I am forced to remove, I will remove it with the swaps. Okay. And how do we change this? If yes, there exists a subset whose sum is S from last I elements, what is the minimum size of it? Because we want to minimum number of swaps, right? Minimum size of it. Remember, for prefix we are keeping the elements. For suffix, these elements are going to be brought from right to left. So that's why the elements that we are going to keep, we need to maximize that. The elements that we are going to bring from the right, that we have to minimize. So okay, so let's say that these have been processed. Okay, so now let's modify this as well. Instead of building segment tree to check if a value exists or not, we are going to do minimum range minimum query. So basically what I am, let's say that there exists some values SR. So earlier it was telling me that if SR exists or not. Now what it is going to tell me that among all of the possible SRs that do exist, X minus SL, Y minus SL that do exist, find the minimum of all of them. So let's say SR, the range L is equals to 2, R is equals to 10. Okay. So L is equals to 2, R is equals to 10, and let's say SR is equals to 4 was possible, 7 was possible, and 8 was possible. So 4 was possible, let's say with 2 elements. So this is what I'm talking about. What is the minimum size of it? So let's say I was able to get the sum 4 with 2 elements. I was able to get 7 with 5 elements. Okay, let's say elements, and let's say I was able to get 8 with 1 element, possible with 1 element. So I would definitely choose 8 1, right? Because these are all valid SRs and I want the right side to be minimum. So I would find the minimum among them. So I would take this LR, instead of just telling me one yes or no, it is going to tell me the minimum among them. So it will give me, for L is equals to 2, R is equals to 10, this is going to give me 1. It says that if you want the sum to be between L and R, there exists a sum which is possible with only 1 element. So I say yeah, good for me. I'm worried about the minimum number of elements. So yeah, because the condition LR, since I am querying between LR, I am already taking care of this condition. I have already taken care that the sum is going to be, final sum is going to be between this one, and total sum would be between X and Y, because SL is already fixed. So now I am worried about just the minimum elements. So what is this is minimum elements from left. So this is it, minimum elements from left. Okay, and what is the maximum elements from left that we can keep? Sorry, from right, what I'm saying, right? Yeah, so this is the minimum elements from right that we are going to bring it into the left side. And what is the maximum elements from left that we are going to keep? That is simply the prefix, right? We updated the prefix I comma SL. Yeah. Okay, so So what happens is, from the left side we are going to keep max elements from left. So how many we are going to remove? So elements to be removed from left, that is equals to I minus the maximum elements that we are going to keep, right? Because whatever you are not keeping, you are going to remove it. So I minus max elements from left that are going to be kept, these are the ones to be removed. So it can happen that what I want to remove from left, the number of elements, that is not equal to what I want to bring in from the right side. So it can happen that, but the idea is I will prove it that what I want to say is that there is always a position where you will find them to be equal and optimum. So we can do is we can say that answer equals minimum of answer comma. So we have these minimum elements from right. We have these many elements that want to come in from right side to left side, and we have these many elements that want to go from left side to right side. So we can take maximum of them. We can say that maximum of them, these are the number of swaps we can take. So this is a bit of a leap, so I'll explain, and we can prove it as well. Elements to be removed from left. So these are the ones that want to come to the left side. These are the ones that want to be removed from the left side. So the maximum of them, I can say that I'm going to do these many swaps. Okay, so so this is one of the solutions. I will prove it, but I hope the solution is clear. What we did was, this is n square log n. Why? Because we fixed the prefix, we fixed the sum from the left side, and then we made a segmentary on it, and the segmentary we did range queries and all that. So that is one log n only. So basically we eliminated one of the this values that we were keeping, the number of elements. So basically we just reduce it to minimum maximum. So I hope this is clear. We will discuss the proof, don't worry. So okay, so we will discuss the proof now. I have to check the questions here.
Understanding data structures and algorithms is difficult.
The proof now. I have to check the questions here. Okay.
Understanding data structures and algorithms is difficult.
No questions I see, so sure. Okay. So I'm going to give the proof now. So let's say we were worried that these the elements that we want to go from the left side, that these are the elements that have to be moved to the left side. These are the elements that have to be brought to the left side from right side. So let's say if these are not equal. Okay, so let's say 3 elements from the left want to go to the right, they have to be removed from the left side. 5 elements from the right side want to come in. Okay, so this is a partition. Let's say 3 elements have to be moved to the right side, 5 elements have to be moved to the left side. Okay, so these are not equal. So what happens then? What we can do is, when we can simply move our I to I plus 1. So what will happen? So what will happen is, this I plus 1 element is now brought to the left side. Okay, so this I plus 1 element is now getting brought to the left side. So it can what can happen is, either this I plus 1 element was one of the elements which had to be brought from the right to the left. Okay, so I plus 1th element, there can be two cases. I plus 1th element was one of the elements to be brought to the left. Okay, or it can happen that I plus 1th element is one we don't care about. I plus 1th element is one we don't want. Okay, so we don't want, we are just simply ignoring it. So what will happen is, if it is one of the elements that wanted to be brought to the left, so good, we already brought it. So what